So acids and bases and salts. When we talk about acids and bases, and we talked a little bit about it last topic, and I said, hey, have a little faith when we do the ionic equations that we'll have some neutralization reactions occurring. And you'll get to see that a little better, not necessarily today, but in probably next week. I don't think we do it tomorrow, but we'll see. All right, so we've got the blanks here. All acids and bases are ionic compounds. So I'll identify how you can recognize when you're looking at an acid or looking at a base. I don't think we do that today except for the Bronsted-Lowry bases. But again, these are ionic solids that dissolve in water, and acids behave a certain way, bases behave a certain way. And we'll talk about those, the way that they behave here shortly. Some characteristics about acids. All acids do conduct electricity. They're ionic compounds. They taste sour. Now, what I don't want you to do is get some hydrochloric acid and go, yep, that's sour. However, we do have a lot of things in our diet that we generally like to partake in that do taste sour. So like all citrus fruits, that has acid in it, and it does taste sour. They all react with active metals to produce hydrogen. And again, we're not going to get into that a whole lot this year. They neutralize bases. And if we had some litmus paper, if we dipped the litmus paper into the acids, it would turn the litmus paper red. Also, we could use some indicators, and I'll do a demo later on when we talk about a titration reaction. An indicator helps us to determine when we're at a certain pH. Now, the type of indicator that we'll be using is generally just a little above 7. And hopefully you can recall back from when you were in junior high about pHs. If I have a pH of 1, what does that indicate? I have an acid. And if I have a pH of 14, then I have a base. And if I have a pH of 7, then I'm neutral. Okay, so you have a general knowledge of what the pH scale deals with. We're not going to talk about the pH scale today, all right? But at least you have some background in that. When we look at bases, or I'm sorry, here's some common examples of some acids here on the left here. So citric acid, that's probably the one that we're most common with, at least with the common name, and that's in your citrus fruit, like oranges, grapefruit, some of your candy that is really sour. Acetic acid, a lot of you may not know what acetic acid is, but you use it quite a bit. It's vinegar. Okay, so acetic acid is in your salad dressing and a lot of other things that we use. Some really common acids that you may have heard about, hydrochloric acid, sulfuric acid. So those are just some examples. Bases, very similar to acids in that they do conduct electricity. However, these taste bitter. In other words, if you've ever had your mouth washed out with soap, okay, soap is a base and it tastes bitter. I don't know if parents do that anymore. I just take the iPad away. But feel slippery. Soaps feel slippery when wet. Also, bases neutralize acids and change litmus paper to blue. Some common examples, sodium hydroxide, potassium hydroxide, and probably one that you don't really recognize, but it is a base, ammonia. Okay, so if you have goldfish, then you know that your tank has a lot of ammonia in it. Some acid and base theories that we'll talk about 2 today. The first one is called the Arrhenius Theory. The Arrhenius Theory deals with the removal of a hydrogen. And one of the ways that we can recognize that we're looking at an acid is if the compound starts with a hydrogen. So if you notice a hydrogen as the first element, you're looking at an acid. So hydrochloric acid. And then to look at a base, if it ends in a hydrogen, then you're looking at a base. So if it starts with an H, that's an acid. If it ends with an H, it's a base. Okay. And I think these are pretty common to what you may have learned earlier on. But the Arrhenius theory simply states that if I'm looking at an Arrhenius acid, it'll dissociate and we'll have some hydrogen ions in solution. If I'm looking at an Arrhenius base, like in the case for sodium hydroxide, when it dissociates, I form hydroxide ions. Okay, so bases are what we associate with hydroxide, acids with the hydrogen. Okay. Here is something that we won't really talk about a whole lot in here, but we'll just beat it to death in AP. but how ammonia behaves as a base, it actually doesn't have any hydroxide in the compound, but what it does to water, and this is what a lot of other typical bases do. Remember how we wrote water as HOH, where we had a hydrogen ion and then the hydroxide? Well, what ammonia does is it rips a hydrogen off of water, and after we rip the hydrogen off of the water, we're left with OH. So as a result, since ammonia produces OH, even though it doesn't break off and form OH, as long as we're forming OH, this is considered an Arrhenius base. Okay? So that's one of the weirder ones. And again, I will make sure that on the test, it's very evident that if you have a hydroxide at the end, then it's going to dissociate, and we'll leave a hydroxide. We don't. This is more of an AP topic, but I just wanted to introduce that.
Is there an Arrhenius salt?
An Arrhenius salt? No. There's an Arrhenius acid and an Arrhenius base. But when you put an acid with a base, we form a salt. Okay. Bronsted-Lowry. This is the other one, and this is where we'll spend a lot of time working on. It's not too bad. When we talk about Bronsted-Lowry acids, we're actually looking at proton donors. Okay? If I donate something, like if I'm going to donate my clicker here, I'm going to give it to somebody. So I would be considered an acid if I gave that away. If I'm a Bronsted-Lowry base, I accept that hydrogen ion, or I accept the clicker. So to identify who an acid is it giving away a hydrogen or accepting a hydrogen? Okay? And then if it's a base, is it accepting it? And we'll do some examples here. And I think we're almost done with the notes today. Now I have a diagram here because once something is an acid on one side, it can have a reversible reaction. In other words, reactants form products, and then the products turn around and form the reactants again. And we haven't talked about that, but that's kind of like an equilibrium system. If the ammonia accepts a hydrogen from the water, and again, probably would be better written as HOH. If it accepted that hydrogen, then we form what's called ammonium, one of your 10 polyatomics, and we're left with hydroxide. If we want to get the reaction or have it move in a reverse direction, what is the ammonium going to do to get it back to where it began? Well, the ammonium is going to donate a hydrogen to the hydroxide. So since the ammonium is on the product side, it was formed from the initial reaction. Since it's on the product side and it's donating hydrogen to the hydroxide, we can't just call it an acid, but we have to give it a secondary name, conjugate acid, which means that the conjugates are always on the product side. Now, these things can act like an acid or a base, but acids and bases are only on the reactant side. Conjugate acids and conjugate bases are only on the product side. So if I'm asking for a conjugate, I'm guaranteeing you that it's actually on the product side. Now, if I say something behaves like an acid, it could be on either side. But if I say identify the acid, then it's on the reactant side. Okay? That's probably a little confusing until we do some examples. But conjugate pairs, again, are always considered products. And whether it's an acid or a base, again, follows the suit. Is it donating a hydrogen or accepting a hydrogen? Okay. And I promise we'll do some examples here. We do have a couple practice problems, and I'd like to work those out with you. Okay. And the first one, the first practice problem says, determine the Bronsted-Lowry acid, Bronsted-Lowry base, the conjugate acid, and conjugate base for each of the following reactions. And you had this, and it's on page 4. So we're given H3O-PO4, and you don't know the name of that yet, but in a couple days you'll get to know that. That's actually phosphoric acid. And I did write the water as HOH just to make it easier for you. And then we have H2PO4 with a -1 charge, and then I don't know what that's supposed to be, but that should be H3O + 1. So change that to H3O + 1. That's awesome. The hydrogen just mysteriously disappeared. Alright, so when we look at this, we have to ask ourselves, I'm going to rewrite this so I don't write it up. So we have H3PO4. And actually this should be a double arrow here. For you guys, no. But I want to be as accurate as possible. All right, so here's how we can determine who the acid is, who the base is, who the conjugate acid, and who the conjugate base are. Look at the before and after. So here we have H3PO4. Over here we have H2PO4 with a -1 charge. Going from here on the left side to the right side, did it gain, and when I say it, the compound, did it gain an electron, I'm sorry, a hydrogen ion or a proton, or lose one? Lost one. So what that means is it donated to the water. And this is what I do for all these. I always show the pathway. In other words, from here to here, the H3PO4 lost a hydrogen. Okay? And then just to double check to make sure everything's okay, from here we have 2 hydrogens, here we have 3. So did the water gain or lose a hydrogen ion? Gain. And we all can see that. All right, so if I lose or if I donate a hydrogen, am I an acid or a base? An acid. So the H3PO4 is an acid, where the water is acting like a base. Okay? So we got the left side done. Let's look at the right side. As we go from H2PO4 -1 to H3PO4, did the H2PO4 gain or lose a hydrogen to get back to the H3PO4? Gain. So I go ahead and draw an arrow, which represents that, okay, now since the H2PO4 gained a hydrogen ion, is it acting as an acid or a base? A base. But since it's on the product side, we can't just call it a base, but we call it a conjugate base. And if you want to represent it as just CB, that's fine. Again, remember the conjugates are always on the product side. So what is the H3O plus acting as? Conjugate acid. Very good. Okay. So let's look at the next one. The NH3, and that one is written out correctly, it looks like. So NH3 plus the water yields, and again, that should be a double arrow, NH4 plus 1 and OH. So correct, yeah. That's all it's asking.
Is that how we're supposed to write it?
Oh, shoot, my bad, this is a 3. Say that again, I'm sorry.
Is that how we label it? We just put A, B, and C, A.
Unless you want to write it out, acid, base, conjugate base. Okay, so let's take a look at this. We have the ammonia, NH3, and it goes to NH4 plus 1. Did the NH3 gain or lose a hydrogen? Gain. And so, well, let's come over to the water real quick. Did it gain or lose a hydrogen going from here to here? Lost. So it's consistent. Okay. So looking on the reverse side, the NH4 plus 1, did it gain or lose to get back to NH3? Lost or donated. And again, how you want to use that terminology is up to you. So once you do that, now you can go, okay, so the NH3 is acting as a what? A base, good. And the water is acting as an acid. And over here, the NH4 plus 1 is acting as a conjugate acid, where the hydroxide is a conjugate base. Now, here's something that's kind of interesting. In this problem, water is acting as an acid. Over here, water acted like a base. There's a term for things that can act as either an acid or a base. I don't know if it's in the notes yet, but that's called amphoteric. Okay, and I know we'll say it later on, but amphoteric. So something that can act as either a hydrogen acceptor or a hydrogen donor is considered amphoteric, and that's pretty significant in chemistry. Okay. All right, so the homework that I just passed out, part of your homework, is the ones, and let's just make sure that we're moving off in the right path here. Okay, the instructions are given there, and it's pretty much just like the example I gave. But looking at the first problem, very interesting. We have water reacting with water. Okay. Anytime you see something like that, let's keep them respective. In other words, this molecule, if it's listed first, is representing the first molecule on the product side. Okay. If you see it, keep it respective. If they're the same, I'm sorry. If they're the same, keep it respective. However, doesn't necessarily mean like if I have in number 2 H2SO4, doesn't mean I have to write its conjugate on the first spot. I could switch that up. Okay. So looking at the first one, let's do the first one together. If I look at the water here versus the water here, looking at keeping it respective, did it gain or lose a hydrogen from here to here? Gain. So we can all draw an arrow there and put an H plus. So the water on the reactant side, the first one is acting as a what? Base. Very good. And then the second one is acting as an acid. Okay. And then on the flip side, going from here to here, did it gain or lose? Lost, because it went from 3 to 2, right?
Okay.
And that's one reason why I always draw the arrows, and not everybody draws the arrows, and you don't have to either. But if it helps you, that's probably not a bad idea. So what is the H3O plus acting as? Very good. And the hydroxide is a conjugate base. Okay. So that's what that is. All right, now let's look at the next practice problem. Still on page 4, down here. And I've got a couple more examples, I think. Yeah, I do. Because this one's probably a little more confusing than normal. All right, so it says the following substance acts as a Bronsted-Lowry acid in water. Write the chemical equation that illustrates the reaction with water. Okay. So what that is saying is, okay, well we have HCO3 -1. Okay. And this is acting as a what? Acid. So we already know it's an acid. Okay. You know it's an acid. I just told you it was an acid. So if it's reacting with water, water is behaving as a base. Very good. So if you want to draw your arrow, that's fine. Okay. Now, here's the fun part. On the product side, if HCO3 with a -1 loses a hydrogen, what will be produced? CO3, what's the charge? Okay, it's -1 here. And it lost a +1 charge, -2. And this is one of your 10 polys. So when you see carbonate, you're like, oh yeah, it's got a -2 charge. Okay, it's just reaffirming everything. And then what is my other product? H3O plus. Good. And don't forget the charges. Okay. Well, it's no charge here, remember. So you have your +1, -1, which equals 0. And then if we add that 1 hydrogen, it's a +1 charge. And then make sure, very good, that's a good point, make sure that your charges add up to be the same on both sides. They don't have to equal 0, but they have to be the same. So if I have a -1 charge for my bicarbonate, that's HCO3 with a -1 charge, and I have no charge for my water, and I have a -2 for my carbonate, and I have a +1, what's my total charge on the left side? -1. What's my total charge on the right side? -1. So we're good. So that's another check that you could do to make sure that you have the same charges. Yeah.
Do you have to label the acid and bases and conjugate acid and bases?
Actually, it doesn't ask you to do that, but if you want to practice, that's fine. So what would the CO3, just because you asked, what would this be, the CO3 -2? Good, conjugate base.
So the bases lose the hydrogen, right?
Bases accept the hydrogen.
Okay.
Yeah, they gain it. So they should have one more, okay, from here to here. So if it accepts that hydrogen, and that's why I always draw the arrow with the hydrogen, because for it to go from here to here, it has to accept one. From where? Could be water, could be another thing nearby. So in this case, the H3O plus is acting as a conjugate acid. Okay. I think there's another one. Yeah, sorry, the instructions are here. It says the following acts as a Bronsted-Lowry base in water. Write the chemical equation that illustrates the reaction with water. So we have our so here HCO3 the HCO3 is acting as a base. So we know it's acting like a base, so call it a base. And if it's reacting with water, what is the water acting as? Acid. Okay, so that means that's the way the hydrogen's going. What's going to be on the product side?
Same thing. The carbonate.
Okay, the carbonate, but it's accepting a hydrogen. H2, good. So H2CO3. And what's the charge on H2CO3? If it's a -1 and we gain 1, no charge. Very good. Bounce is written. And then if the water loses a hydrogen, what will we write on the product side? Hydroxide. And what's the charge on hydroxide? -1. So we have a -1 plus 0 equals a 0 plus a -1. So we're good. Okay. Does that make sense? You want to do a couple more examples? Okay. Let me do one more since I've got it here. Okay. And these are not in your notes, but if you want to write in the margins, that's fine. Okay. These first two are acting as acids in water. So if I place, you don't have this in your notes. You can't see it? Pull it up. Okay. So H2SO3, that's sulfurous. You haven't learned that yet. You'll learn that next week. Okay. So if this is acting as an acid, what will it do? Lose a hydrogen. Good. So what are my products? Pen's not writing very well. I heard you say something, Kat. What'd you say? If it's good, HSO3, and what's the charge on that, Courtney? No charge here. Loses a +1. -1. Good. And then what's the other thing?
H3.
Yeah. So H3O plus. Now, do me a favor and don't write this. Okay. Don't do that. Actually, if you were doing it, you would write it like that. But just write H3O plus. It'll be easier for you. Okay. All right, and then here, let's skip the HCN because I know you guys already know that. And let's look at the H2PO4 real quick. Or let's go for the jugular. Let's go down here to SO3, -1. This is acting as a base. So if we know it's acting like a base, what is water acting as? An acid. So what will we have on the product side? HSO3. Actually, that should be a -2. That is a terrible charge written there. So if that's -2, what's the charge here? -1. Good. And what will we have with it? OH. Good. And what's the charge on hydroxide? -1. So -2 plus 0 equals -1 plus -1. Okay. Isn't that exciting? All right. So the homework is.
Lovely wedding band you got there.
Well, thank you. So the homework is that's your 1s and then the 2s. Yep.
Cool.
Should have enough time to finish her.
Yeah, there's only technically 2.